Hi, in this video we'll learn how to do vector addition, and it involves the techniques we learned in the last two videos on vector mathematics. So just to give you an idea here, we've got a table of the vectors you can see, and you can see we've labeled the components here, x and y, for both two vectors a and b, and we're going to add these together to get a third vector c. How are the components related? Well, the way it works out with vector addition is you always just add like components. The x components of a and b are added, the y components are added. Never mix these guys together when you're doing vector addition. If you look at the picture here, we've drawn the vectors a and b, and so we started at the origin here, right? And then what we do is we draw vector A as specified, and then we put the tail of vector B to the head of vector A and draw it exactly as specified, right? Until we get to the end here. And so here's our vector A, tail to head, vector B. And then when we finally draw the resultant vector, C, you go to the very initial point where you started and draw to the very last part that you ended. And there's your vector C. This is called geometric or graphical vector addition. Now what we're more interested here actually is learning how to do the algebraic or component method of vector addition. But the graphical method gives us an idea of how that works. As I said, you could only add like components. So if we look at this here, check out the AX and the BX. They're both positive, and when you add those two together, you get CX, right? Now, conversely, let's check out the AY. It's positive. The BY is down. It's negative. So if I take this one and I subtract off the BY, then I end up with my CY. And that's why we only add like components. All right, let's see how we do this here. So here's an example problem. It's the same vectors as we saw. Now we're going to add a plus b, and we're going to end up with what we call c. The vector that you get when you sum other vectors is typically called the resultant vector, so we'll allow it to be called the resultant vector c. Now any type of vector obeys the same math, and so let's assume that these are velocity vectors. They have units of meters per second. And we've specified vectors a and b in terms of their magnitude, this guy, and their direction. And same thing for b, magnitude, direction. First step, we need to convert all our vectors into component form. We always do that first. So we're going to go ahead and quickly do that because we've seen it in a previous video. Let's start with vector a. All right, so I've plotted vector A. Remember, we start north and move 20 degrees towards the east. Here it is. I've put the hypotenuse on there, and I've chosen to make the triangle that is the upper part here with A, Y, AX. Now we're going to use that to go ahead and figure out the components here. This is where the table method of vector components really shine. So I've set up my table, and now we're going to do the quick process of vector components, right? So look at the vector. First quadrant, right? That means x and y are both positive. So my plus and my plus. Second step, write down the magnitude. 15 meters per second, 15 meters per second. Finally, pick the right trig function. For x, notice that ax, this is the opposite side from the angle of 20 degrees, so that's sine of 20 degrees. And similarly, AY is the adjacent side, so it's going to be cosine of 20 degrees. Now notice something important. I don't memorize cosine is x, sine is y. I look at the picture and I find out that for x it's opposite, it's sine. For y it's adjacent, it's cosine, okay, for this particular triangle. So I've put my answers in from the calculator for vector A, and I've already set up my picture for vector B. Notice I always replot it from the origin and do it in its own graph so I can see it clearly and figure out my components quickly and easily. And so the length, this one again, right, you start at east here, and you move towards the south by an amount 35. The magnitude of this one, the hypotenuse, is 12 meters per second. And we're going to go ahead and figure this out. Which quadrant is vector B in? It's in the fourth quadrant. That means that x is positive and y is negative. Always got to check that. Next, write down the magnitude. 12 meters per second. 12 meters per second. Look at your equation now. Let's look at bx. That is adjacent to 35, so that's cosine for this triangle. And for by, it is opposite of 35, and so that's going to be sine for this triangle. And so I've checked my calculator and I've written down the numbers. Let me clean it up a little bit here for you. All right, before we go on here, I've cleaned up the numbers here for A and B, just what we calculated in the table. We're always on the lookout for mistakes, and so here's how I check for mistakes. Let's look at vector A. Do I have the signs right? Is it positive, positive? Yes, first quadrant, good. Do I have the number sizes right? Let's see. The x component is smaller, the y component's bigger. Look at that. Y is larger than x. The vector itself is closer to y than x, so we're happy with that one. What about the other one? For B, what quadrant are we in? Fourth. That means plus x minus y. Got it. Nice. It's larger in the x direction. That means the vector should be closer to x than y. Is it? Yeah, it's only 35 from x. So we're happy that we got the numbers and signs right. All right, now that we're happy with the vector components A and B, we are ready to get to the next step, vector addition. I wrote the equation for vector addition when you're adding C equals A plus B right over here. And if we look at it, it means that to get Cx, we only add the x components of vectors. Notice here, y, only add the y components. If you write an equation like this, make sure it's all x or all y, right? Don't mix them. All right, what does that mean? Well, for our table, this is where it really shines. We just go ahead and we just straight add the two x components. And then later we add the two y components. And doing that, we're going to end up with our x component of C and our y component of C. So if I add 5.13 plus 9.83 meters per second, I'm going to get here 15.0 meters per second with rounding. And the other ones, when I add the column below y, I end up with a 7.22 meter per second. So now we know the vector components of C. There they are. But we're asked for the magnitude and angle. So we're going to have to convert this to magnitude and angle. What do? Well, we go ahead and plot that vector C, and then we go ahead and use our trig, just like we did in a previous video. So I've drawn a coordinate system, and I'm going to plot C. So I know here is the x component of C, 15 meters per second. And here is the y component of C, 7.22 meters per second. We look for that point in the plane. There it is. That's the tip of our arrow. Let's draw C. There it is. And let's go ahead and draw the vector components of C. There they are. There's our right triangle. Here is the magnitude of C right here. And here is the angle that we want to solve for. So we're going to go ahead and do the magnitude using the Pythagorean theorem. So this is going to be 15 meters per second squared, Cx squared plus 7.22 meters per second squared, Cy squared. Put that into your calculator and you're going to get 16.6 meters per second. So that's the length of this arrow. And finally, we're going to go ahead and get the angle here. We'll use the tangent inverse function. And so that's going to be opposite, right? From this angle, here's your opposite, here's your adjacent. So we're going to take the CY, 7.22. Remember, I could ignore the sign and the units. And then I'm going to divide by CX, which is my adjacent. and I'm going to have that at 15, and when I put that into my calculator, I'm going to get about 25.7 degrees. That's what this is. And if we think about that, we are already starting at 0 degrees. Here's 90 degrees, and when we start from 0 and go counterclockwise, we get to that point. So this is already counterclockwise from plus x. So we've just figured out the magnitude and the angle of vector c. Now, if you were asked to do this same direction in the cardinal directions, we could do it like this, right? Here's east, here's north. We start east, and we move north 25.7 degrees, go backwards, start east, move north, how much? 25.7 degrees. It's another way to write the same direction.